All right, are you guys ready? I've got another story. Long story.
Can I just ask a quick question?
Yeah.
Just hypothetically, like you could use this for system estimation too, kind of if you have known states and put the states that you're trying to observe here as your states that you're estimating. You can kind of do parameter estimation that way,
huh? I don't think I quite understood your question. Fu, do you mind shutting the door for me? Thank you.
I was thinking about like how you come up with the state models for a lot of this stuff, right? Because the accuracy of your optimal tracking depends on the state model that more or less fits your process, and you can cheat that a little bit because of the stochastic noise. But in general, if you have the wrong process model, you're sunk before you started.
It's a really good question, and it turns out it's kind of one of those questions that has a long-winded answer. Let's say you've got a very simple model that is just first-order autoregressive, where we say there's some alpha times x of n plus, let's say, some noise. And let's presume you've got a good idea of what the process noise variance is. But let's say that you've got no idea what that alpha is. Well, I don't know what it is. Let's just fold that into the state vector and make that part of the state. So we'll make that now time varying, and now we need a model for what that parameter is. So we could say alpha of n plus 1 is equal to something. And if it's a fixed parameter, which I think is what you were alluding to, one model could be that it's just equal to what it was at time n, which conveys that we've got something that is unknown, but it's not time varying, that it's fixed, but we just don't know what it is. So then how can the model adapt that when we've got it kind of constrained, where we're not really even adding any process noise? We say it's just fixed. One way is that when you're initializing this at time 0, we say we have very high uncertainty on what that parameter is. And so you can fold that in, and then you say, well, oh my gosh, this is really powerful, because now I can do parameter estimation by just extending the dimension of the state vector. And there's no penalty because I'm doing Monte Carlo integration, so let's go crazy. And whenever there's something that I'm just not quite sure what it is, I'm just going to ask the particle filter to do its magic and estimate it. And you can tell by the way I'm describing this that in practice that doesn't always work. And it doesn't work because the more things that you're trying to have the particle filter estimate, the more variability you're going to have in those estimates. And so we want, as engineers, we're trying to design these state space models so they're as simple as we can possibly make them, while at the same time having enough complexity in them that they model the dynamics that are relevant to our process. And so there's a balance there. And we deliberately, oftentimes, will simplify things and sort of like lump noise together into this process noise term rather than having a bunch of terms with different parameters that we try to estimate, because those estimation problems can be hard. And it depends also on how they're related to our measurements, how kind of observable the state is. So there's a balance there, and ultimately I think it comes down to good judgment. But this class is most of the lecture time is spent on the algorithms, but the algorithms are kind of cooked. They're already done. You're learning what they are. You now know that simple resampling particle filtering algorithm, which is the most powerful one, really, that we'll talk about all term. But as engineers, the reason that you're paid well and we're going to contribute a lot of value for the applications you work on is in really careful model design. It's in coming up with those model designs and validating them. That's where you can really add a lot of value and really improve the performance of your tracking. So you have to think about all that really carefully, and it's not easy. I'm just giving kind of general guidance. It depends on the application. I struggled with that in my own research and applications as well. But this set of slides is more about something that has kind of a good answer. There's kind of a neat story to the set. I don't know if we'll get through this today or not. So one of the things I sort of glossed over is I said, look, you're the engineer, and the theory works no matter what you pick the importance density to be. We make one decision kind of early on. We know by Bayes' rule that we can factor our importance density for the entire trajectory this way. This first step here is just Bayes' rule, where we're taking the joint probability of the entire trajectory and we're breaking it up into the component at time n, and then the rest of the past trajectory from 0 to time n minus 1. So this first step is just Bayes' rule. There's nothing special about that. But then when you're reading through the tutorials on particle filters, you see again that this n ends up being an n minus 1. You're like, where did that come from? Well, where that comes from is that suddenly makes this so that we can advance these particles forward in time without having to regenerate the entire trajectory. If x of 0 to n minus 1 doesn't depend on the nth measurement, it only depends on the past measurements, then I don't have to regenerate that entire trajectory again, taking into account that nth measurement. I can leave it alone and simply take whatever particles I happen to have, or particle trajectories I happen to have, from 0 to n minus 1, and then I can advance them forward with whatever this ends up being. And this is the importance density in this part of it in its most general term. And what I used when we were talking about particle filters, I said it's up to you. Look, I'm just going to arbitrarily choose the prior because it's easy, and make this x of n given x of n minus 1. I'm sorry, it's hard for me to write on a tablet this way, but I think it's good enough that you can make it out. So we chose that, but really we could make this part of it anything we want to be. The reason that this is n minus 1 is just so that we can calculate our weights recursively and we can move these particles forward recursively. And that's really important for real-time applications especially. You don't want the computation to increase as time goes on. And it would if you're doing it this way, because every time you get another sample, you have to regenerate the entire trajectory and go forward all the way to time n. And that doesn't work. We're engineers, and we need things that can be done recursively, that could run indefinitely without the computation increasing with time. So with that one choice, we end up with a weight update equation that looks like this, where again I've got the importance density in its most general form. And it would seem, based on what we learned, where the number of effective particles seems to rapidly degenerate when we choose the prior, let's revisit that decision. I said you could choose anything you wanted to, which is true theoretically, but we see, you've now seen the problem with choosing poorly. The weights rapidly all go to 0, and then you have to resample. And resampling uses our computation, and then we can't have as many particles, and it's not as elegant. So is there a way that we can pick this a lot better, that importance density a lot better than what I happen to choose in my examples? That's the question at the outset of this set of slides. And again, the easiest and the most common choice is just to pick the prior. Usually you come up with a state space model where you're going to be generating synthetic data anyway, and if you're able to synthesize data with it, then you can certainly use this as your importance density. So it's really convenient. You're usually already running your process model with synthetic data, so you can make sure that your tracker works well with synthetic data. So this is handy because we need that from our importance density. We need to be able to draw samples from it. And as Walt said earlier, probably based on the reading or maybe based on math, when we plug that into our weight update equation, where we've got the prior for our importance density, this is our importance density, and when we put it down here, we get a cancellation. This ends up being, canceling those two, and so we end up with our weight update ends up being what the weight was simply multiplied by the likelihood. So that simplifies, which is kind of nice. Then we don't have to even evaluate this PDF wherever the particles land. The only thing we have to be able to evaluate is this likelihood. And I have to give you one word of caution. I should have mentioned this earlier, but students always get tripped up on this. This likelihood is going to bite you, and it's a numerical issue. When you, for those of you that are working in MATLAB, I don't know if this happens in Python, but it probably does. A lot of you are going to use Gaussian measurement noise. And if your process model, if this is your importance density, and your process model is pushing the particles far away from what's consistent with your measurements, then when you evaluate this likelihood function, and if it's a Gaussian, this may end up being where the measurement is many standard deviations away from the mean, And numerically, MATLAB may say, that's 0. It's not 0. It's never 0. But numerically, it may be such a small number that MATLAB returns exactly 0 numerically. It's just a finite precision effect. And so then you go through, you code in the algorithm, and you go through and you're doing your weight updates, and after a while you realize all my weights are ending up being exactly equal to 0. And theoretically they can't be, but numerically you're finding out that they are. And it's because either your measurement noise is so small that your particles, all of your particles end up being far away from it, and numerically this gets being evaluated to 0. And of course 0 times something that's non-zero is still a 0. All your weights are 0. And then usually where that hits you in the algorithm is when you're trying to normalize your weights and you divide by the sum of the weights. The sum of the weights ends up being 0. All of your particles end up being far enough away from your measurements that when you evaluate the likelihood, it's exactly 0. And when you normalize, you get a divide by 0 error. And then suddenly you get not a numbers, and your plots are all screwed up, and you're unhappy, and you're sending me emails and coming to my office hours saying, my code's not working, I don't know what's going on. So that happens frequently, and I wanted to warn you before Monday. And I do have office hours on Monday, but hopefully now you won't need to come see me about that if you're working on this over the weekend. So that happens often, and the solution is don't push your particles so far away. Choose something different for your importance density, or turn up your measurement noise so that some of the particles are within range, and it doesn't evaluate to 0. But that was a digression. The main point is this is a common choice, and it just completely ignores all the observations you have. So when you're doing this, you're moving your particles forward sort of blindly, in the sense that you're not listening to where your measurements say they ought to be. You've got access to your measurements, but for one reason or another, you've chosen to ignore them in moving your particles forward from time n-1 to n. You're just doing it based on the process model. And that can kind of get you into trouble. You're kind of exploring your state space without any accounting for the measurements that you have. It's said this can be sensitive to outliers. You'll read that in some of the reading that you have. But the nice thing is it's really easy to implement, and it makes evaluation of the weight updates really easy. All you need is to be able to evaluate your likelihood. And I mentioned this before, if you use this as your importance density and you resample at every step, that sometimes is called the bootstrap filter. It's just a name, but that is a design decision that could be made. And students who've taken this class previously, some of them just say, I don't care, I'm just going to resample every time step. I don't ever want to have fewer than the maximum number of particles I can working for me. So it's not unreasonable or unusual to make that decision. But that's up to you. What would have been an even easier choice is to just ignore everything, ignore the prior state trajectory as well as all your measurements. Just forget it. Use Gaussian, use a uniform distribution. Use anything you want. The importance density is up to you, and you really can use anything you want. But you can predict what the problem's going to be. If you're just using numbers randomly drawn from some random distribution where it has nothing to do with what the state was at time n-1, it's very unlikely that you're going to be choosing, you're going to be moving particles forward in time where they're consistent with a prior, where this is significantly larger than 0, and are also consistent with the likelihood. And so your weights are very rapidly going to go to 0. You'll hit that degeneracy problem almost immediately if you try to do this kind of fixed importance density. So theoretically it's sound, but practically no one does it. You're sort of randomly poking around in the state space, and it's far worse than picking your prior as your importance density. So I don't know why anyone would actually do that in practice. Because I don't know of any good reason to make that choice, even though you could make that choice and the math holds up. And if you have an infinite number of particles, it will work just as well. But no one's got an infinite number of particles, even in 2016. So ideally, what we'd really like to happen is to have these weights all be 1 over np, have all the particles contributing equally. That would be the best case, because then we really are taking an average, and it converges the most rapidly with the fewest number of particles, and life is good. So ideally, we would really like the weights to all be constant, to all be 1 over the number of particles. We've got to sum to 1, so if they're going to be equal, then the only thing they can be equal to is 1 over the number of particles. So that's what we would like. So one of the things that you see in all the tutorials and the books on particle filters is this idea of, well, we get to pick the importance density, we get to pick this thing, so let's pick this thing such that the variance of the weights is minimized. You know, the weight is determined partially by the importance density, and so let's pick that importance density so that when we calculate the variance of the weights, you know, ideally they're all the same thing and have a variance of 0, so let's minimize that variance. That's the idea. So if we say, okay, we make the importance density anything we want. If we're going to calculate a variance, first we have to know what the mean is, because the variance is, you know, expected difference between the weights and their mean. So let's figure out what the mean is. The mean, if we plug it in, you know, for our importance density, you know, we're looking at the distribution across that importance density, then we end up with this expression. The variance is given by this expression, and again, let's try to minimize that.
Is this variance computed over both I and n? Like one number for all weights or all time?
It's an excellent question.
Is your importance density different for each weight? Or each state?
It is different for each particle because it's conditioned on what the particle was. And the fact that, you know, for a given particle, this is going to be indexed by I. So this will be for what that particular particle was. So that does make the importance density different for each one. Yeah, that's true.
But it's not necessarily conditioned on what a particle was in the past. It's really also conditioned there on what the expected value of the actual value was, right, for that state. That's not just what the value of that particle was. I guess it's kind of saying the same thing.
Andy, I didn't quite catch that.
I guess when you're picking that Q, right, it's going to depend not just on what the past values of that particle was, but what the expected value of the state was at that previous time point. So when we're doing this expectation, it's across the ensemble of possible states, not just possible particle values.
Well, but it's conditioned on those things. It's not across the expectation of those things. So, you know, based on what the trajectory has been for that particle and what your measurements have been, this particular expectation is over only the state at time n. You know, we're going to be advancing the particle one step forward, and then we'll evaluate the weight based on where that lands. And so this expectation is only taken over the state of the values that state could take on at time n. And that is for the ith weight. So I probably should have indexed this by I and that by I as well. I think that's the answer. So, and I'll circle back to this. I mean, some of you may have read ahead and be asking me hard questions right now when I didn't want you to quite yet. So, cut me a little slack and bear with me as I kind of walk you through this math at a high level. So this is just the weight update equation that we've seen many times before: likelihood, prior, importance density, what the weight was at time n minus 1. And if we look at the expected value of that weight, again, across our importance density, which is only the part of it for the what the state could be at time n, then if we plug in the equation for the weight, this recursive equation, we can pull out this term, the weight at time n minus 1, because it's a constant, and we end up with all of this, but fortunately we get a cancellation. This importance density cancels that one, and so we end up with just the likelihood times the prior. And because this is a Markov process, we usually don't do this, but in this case I'm going to. because this is a Markov process, whether we condition this on x of n or x of n and x of n minus 1, we get the same probability. So I'm adding something that it's being conditioned on, which I can do because it's a Markov process. And when I do that, this now can be written, because these are both conditioned on x of n minus 1, this can be now written as a joint probability of y of n and x of n conditioned on what the state was at n minus 1. But we're integrating out x of n, and so we end up with something kind of like the likelihood, but it's a little bit different because it's conditioned not on the state at time n, but the state at time n minus 1. It's the probability of that measurement conditioned on the measurement at time n minus 1. It's weird, but bear with me. That's what we end up with. So that's what the mean of the weight is equal to. We haven't answered our question yet, but bear with me. At least now we know what the mean is of the weights. Okay, so we also need the variance. Again, this is the weight update equation here, and the variance is given by the expected squared difference between the weight at time n and the mean. And another way that that can be written, that you've probably all seen many times before now, is that you can also express this as the expected value of the squared value of the weight minus the squared value of the mean. It's fairly easy to multiply this out and take the expected value of the different terms, and after doing a little bit of math, you arrive at this equation. And we've got an expression now for what the mean is, and I'll substitute that in a few minutes. But let's look at this first term of the expected value of the squared value of the weight. So again, we plug that in. This is just our importance density. We've got an expression for what the weight is. So if I square this whole thing now, I end up with a weight at time n minus 1 squared, but that's not a function of the state at time n, so I can move that outside the integral. We've got the square of the likelihood times the prior divided by the importance density squared times the importance density, because that's the probability that we're taking the expectation over. And that gives us, again, a cancellation. I can cancel this with one of the terms in the denominator. And so we end up with this expression. And the mean is, we know from the previous slide, the square of the mean can be written as the previous weight squared times the square of this thing that's a little bit like a likelihood, but it's n minus 1. And this should have been, I see now that I've got an error, this should have been conditioned on. And this should have been conditioned on, not a comma. It's not a joint, it's a conditional probability. So stick with me. I know all of you could go through this math on your own, and if you're not following this fully, you can take your time and go through it on your own. I think the steps are easy enough. You could do it fairly easily. So let's suppose now, I'm gonna propose an importance density, which is the probability of the state conditioned on both the state at time n minus 1 and the measurement at time n. So it's just a proposed importance density, and let's calculate what the variance is given that importance density. If we do that, and we substitute now this in for our importance density in the denominator, then we get this expression, we get this term. And I've also written the likelihood, I've expanded it so it's conditioned not just on the state at time n, but also the state at time n minus 1. And again, I can do that because it's a Markov process. And if I do that, then again, I can combine these two terms by Bayes' rule and write that as a joint probability, as I did before. And then I can apply Bayes' rule one more time and expand that out so that this now becomes the probability of the state at time n conditioned on the state at n minus 1 and the measurement at time n times the probability of the measurement at time n conditioned on just the state at time n minus 1. And the reason that I did all that was to get a cancellation where this term in the denominator will cancel one of those. So I know it's a lot of math, but bear with me. It's worthwhile, sort of. So this is just a copy of the last equation from the previous slide. Again, this can cancel one of those, and so we end up with just one of those terms times this other term that we had before. We're integrating all this with respect to just the state at time n, so this term can actually be taken outside of the integral. And so we end up with an integral of a probability. The integral of a probability is just 1 because it's a probability. There's nothing else there. So this whole thing is equal to 1. And so we end up with this term minus that term, but this term is that term, and so finally we end up with a variance equal to 0. Now, I know that was a lot of math, and it's just calculus. I think all of you are capable of doing it. But I went through that because I saw that when you use this as the importance density, there's one of the famous papers says you go through straightforward calculations and you can show that the variance is equal to 0. And it took me like hours to figure out what on earth they were talking about and what these so-called straightforward calculations were. But after I did the work, I felt like I should record that for my students so that they're also not tripped up and trying to work their way through all this math and arrive at that result by just doing some straightforward calculations. But those are the so-called straightforward calculations, as best as I can tell, that shows that with this particular importance density, that the variance of the weights is equal to 0. So, ta-da, here is the optimal importance density, or at least that's what the papers say, and it means that we have no variation in the weights, so it's great. Now you know what you want to use. We've got the importance density. So what are the importance weights in this case? Let's have a look at that. It turns out there's a simplification there too. The importance density, again, is given by this, and if we plug that in to our weight update equation, so we're going to substitute in our new importance density here, we can combine the two terms in the numerator, because this is conditioned on the state at time n, and again I'm going to extend that so it's the state at time n minus 1 as well. So here we've got the joint probability again, same thing I did with the integral. And then I can break that out a different way by Bayes' rule, where we've got the state at time n conditioned on these two things, multiplied by this thing that looks kind of like a likelihood, the probability of y of n, but again conditioned on x of n minus 1. And we end up again with a cancellation. This term cancels this term, and so after all this, what we end up with is again a very simple weight update equation, where we just have this thing that we multiply the previous weight by. So now I have to tell you when I was studying particle filters and trying to figure out how these things work and trying to understand it, I was scratching my head when I was reading the sections about optimal importance density, because I thought I already knew the answer before any of this started. We knew at the outset that if we could draw particles from the true posterior, that we wouldn't even need weights. We could just take sample averages. It's equivalent to saying all the weights would be 1 over the number of particles. And we said, we wanted to do that, but we can't draw samples from this. But that was ideal, that was optimal, was the posterior itself. That's what we wanted to draw samples from. And now we just went through and did a lot of math, and we ended up with a different answer, where the importance density now, or at least part of it, is given by this equation. And how can they both be optimal? It took me a while to kind of puzzle through this and try to get a sense of what was happening here. And keep in mind, this could have been conditioned on the entire past, but after all our math, it ended up being only conditioned on what the state was at time n minus 1 and what the measurement was at the current time step at time n. But again, something seems wrong here. We said we're going to minimize the variance of the weights. If you're minimizing the variance of the weights, shouldn't it all be 1 over np? But the optimality criterion that I was hoping you wouldn't ask me about at the outset, because I wanted to say it, is that we were minimizing a conditional variance. The probability that we were using was this probability, and that's conditioned on these things. So all that really means is that the ith weight is unaffected by the variation in x of n. That when we're moving the particles forward in time, that the variation in how we draw those particles doesn't affect the weight, that the variance is independent of just this question of what the particle is going to be at time n. It still depends on the likelihood. It still is influenced by the measurement. And so if we're, it's right here, right? We were taking the variance over this probability, but this is conditioned on the measurement. And that measurement means it can still drive the weights to 0. It shows up right here. So it wasn't. It's not as good as it sounds. You know, when you're reading the tutorial, it's like, here it is. This is the optimal, so-called optimal importance density. But the optimality criterion they chose was kind of messed up, in my view. It wasn't. You weren't really getting what it seemed like you were, you know, as advertised. It doesn't mean that all the weights across the ensemble are going to be equal, which is what I had been expecting when I was first reading this. So then you got to ask the question, well, what did we really gain from using this optimal importance density? That's I think that's a legitimate question, given that we ended up with something where the weights are still being driven to zero because we've got this term. It's not that the weight at time n is equal to weight at time n minus 1, as you probably would have expected when I said we're going to make the variance equal to 0. The weights are still going down. The variance of the weights is still changing. Okay, so I mean, this isn't my story, but it's in the books, it's in the tutorials, so I feel like I have to explain what's going on with this optimal importance density. Let me pause. Any thoughts, questions?
I'm unclear on how to sample from that.
Yeah, that's a great thought. Me too. Me too. So, and yeah, it's one of two problems. That's a great problem. Or it's a problem I certainly agree with. How on earth do you draw from that thing? Even we know the state space model, it's not clear how you would draw from that. It's also not clear if you were able to draw samples from it, how you would evaluate exactly. What is this PDF exactly? We know how to go from the state space model to get the likelihood and how to get the prior, but this isn't either one of those. So one problem is how do you draw samples from it? Another problem is how do you evaluate it for a given measurement, and the state? How do you evaluate what it is? We don't know how to get that probability directly from the state space model. We know how to get it from an integral. We could certainly multiply these two together, and with a little bit of math, you can show that this is just the integral of the product of those two. But there's not usually a closed form solution, so we're back to having to evaluate an integral, and you can't say, well, we'll just Monte Carlo it, but you know, you don't want to go too crazy with that if you don't have to. We didn't have to do that before, so now why would you want to evaluate an integral for every particle? You're going to do a Monte Carlo integration for every single particle. Computation wouldn't scale well in that case, so that's probably not the way you want to solve the problem of how you evaluate this integral. So there's kind of two big problems with the optimal solution, if you accept that it's optimal to begin with, which I'm asking you to not just take because it's written in the well-cited articles and in books. There are some models where you can actually solve for what this optimal importance density is, but they're limited. You know, they're not for just any state space model. And so what some people do is they'll make approximations based on the models that are available where they know what the solutions are. They'll create approximations of those state space models, just like the extended Kalman filter and then Synthetic Kalman filter. I'll talk about those. And basically what we end up with is a local linear approximation of the state space model. And one way of doing that is based on Taylor series expansions. We'll see later when we talk about the Synthetic Kalman filter and maybe even Gaussian sum particle filters. There's more elegant ways of doing this, but Taylor series is kind of the classical way of doing this. So this is probably a good stopping point because you're probably overwhelmed with the math we just went through, and there's a lot more to follow when we talk about the linear measurement model. So let me hold this, and we'll continue this story on Tuesday. But suffice it to say, even with its limitations, choosing an importance density that's equal to the prior, just like I did in the last set of slides, turns out to be a perfectly reasonable choice. I know you guys don't like resampling, I don't like it either, but it works. So just use it. It's not so bad. This isn't going to get you much, despite the stronger theory behind it. So we'll continue that story on Tuesday. All right, have a good weekend.